Another pattern you will notice when studying the unit circle is what happens when you flip a triangle over the x-axis. For example, think about 30 degrees, or pi over 6. If we reflect this over the x-axis, we will end up at 330 degrees. Notice that what happens is the y value, which is 1/2, which is sine's value, sine is y, flips to negative 1/2 when you flip it over the x-axis. Naturally makes sense because it's the same distance away. What that in effect means is that sine will just simply change from positive to negative as you flip it over the x-axis. In effect, then what you're doing is you're just making the y value negative. We can see that this is true for any angle on the unit circle. Let's go to the second quadrant. If we take this trig value at 135, which is square root of 2 over 2, if we flip it along the x-axis, and the y value will become negative square root of 2 over 2. We can do from 150, which is at positive 1/2, to 210. We can even do it for these yellow angles at multiples of 15. For example, sine of 105 is square root of 6 plus square root of 2 over 4. If we flip that, it's the same thing but negative. What we are seeing then is what is in effect confirming that sine is an odd function. Now I know it's been a while since we looked at odd functions, so let's go ahead and explain that. An odd function is when f of negative x equals negative f of x. Now in the case of sine, let's talk about 30 degrees. For example, if I said sine of negative 30 and we looked at the unit circle, we can see that sine of negative 30 is just the same as 330, or negative 1/2. So if sine of negative 30 is equal to negative 1/2, what would sine of 30 be? It would just be 1/2. You're taking the negative 1/2 and you're multiplying it by negative 1 to make it positive 1/2. So therefore, sine is an odd function. You can do this for any angle. Let's say we wanted to do sine of negative 135. Well, sine of negative 135 would actually be the same as 225, which is negative square root of 2 over 2. If we go back and look at our identity, is it the same as negative sine of 135? If we go back to the unit circle, we want to take sine of 35 and make it negative. So sine of 135 is square root of 2 over 2. If we make it negative, we get negative square root of 2 over 2. The same thing that we got down here. Whoops, wrong angle. We get negative square root of 2 over 2. So this proves that sine is an odd function. The same will be true for cosecant, simply because cosecant depends on the y value. It's just 1 over y. So if we start with an angle and look at its negative version of that angle, or flip it over the y-axis, it will be the opposite sine of the original angle. So therefore cosecant is an odd function. Let's take a look at the unit circle to see an example of that. So for example, let's say cosecant of negative 15. It would be square root of 2 minus square root of 6. Now if we flip that and go to 15, that would be the same as cosecant of theta. We get square root of 6 minus square root of 2. They flipped. And if we make that negative, they will be the same. So basically what it means is there's symmetry over the x-axis, except that you get the negative version of the trig function back instead of the positive. The next identity we're going to look at is cosine and secant. Now recall that an even function is when f of negative x equals f of x. In other words, it doesn't matter if you flip over the x-axis, the y values will be the same. So for example, let's look at cosine let's go back to our normal angles. Let's hide the yellow angles here. If we flip cosine of 30 and we make it cosine of a negative 30, we see that the value doesn't change. It's square root of 3 over 2 either way we flip it. Cosine of negative 30 is the same as cosine of 30. If we look at cosine of 45, it doesn't matter if it's negative 45 or positive 45. It's going to be equal to the square root of 2. If we look at 60 degrees, it doesn't matter if it's positive 60 or negative 60. Therefore, cosine of theta is the same as cosine of negative theta. Going back to sine, just because I think it's so important, notice that if we do the same thing and I keep my green highlighter over the y value here, or the sine value rather, sine of 30 is almost the same as sine of negative 30, except it's its opposite sign. That's the easiest way to explain odd functions, is that if you take the negative of the same input, then you get the negative value back. And that's one other way. I will write that at the top of this page. One other way to explain odd functions. It's not typically written this way, but that f of x is equal to negative f of negative x. In other words, what you're in effect doing is you're making the angle, you're flipping the angle, so you're making a negative, but then whatever answer you get back, you're multiplying that by negative again to ensure that those values are the same. So for example, at the angle we're at now, if I change 60 to negative 60, okay, which is the same as 300, what I am in effect doing is changing the sign of my input, right? So I get negative square root of 3 over 2 back. But if I multiply that by negative 1, I get positive square root of 3 to 2 back, the original sine value that I got for sine of 60. That's the easiest way to explain odd functions. Unfortunately, a lot of books, they don't teach it this way. They put the negative sign over here, so it's a little bit more confusing, but it means the same thing. Okay, so since cosine is even, it's naturally going to be the same for secant. If I go back and again, this up here is the definition of odd. So since we're talking about even, we'll just write the definition of even up here, which is that f of, the only difference is it's f of negative x equals f of x. There's no negative in front of the f. But if I switch, let's go down here to my secant value. If I switch my angle here and I go from 60 to negative 60, notice that the secant stays the same. If I go from 45 to negative 45, the secant stays the same. If I go from 30 to negative 30, the secant stays the same. Doesn't matter if I go from 90 to 270, the secant's still undefined. So by making the negative angle, it doesn't matter, it stays the same for secant. Now the last pair are tangent and cotangent, and we go back to being odd. So the way I like to tell my students is the only two even functions are cosine and secant, because they're based on the x value on the unit circle, whereas sine and cosecant, tangent, and cotangent depend on the y value. So let's look and see how tangent and cotangent are odd if we look at the pattern on the unit circle. So for example, let's start at 30 degrees and look at the tangent. The tangent is square root of 3 over 3. So if I flip that to negative 30, I would expect the negative to come back. So I do get negative square root of 3 over 3. And again, this confirms the definition of odd. F of x is equal to negative f of negative x. Again, you could just take this negative and move it over. Whoops, I'm having some issues here. 1 second. You could take this and move it over, and it's the same definition because you're just multiplying by negative 1. But for example, so by making this negative 30, I'm saying negative x, right? But if I make that negative again, if I make that y value that I get, or my answer for tangent, which is negative square root of 3 over 3, if I multiply that by negative 1, I get the original tangent value back. So again, it's just symmetry over the x-axis, except you're changing the sign is what happens when you flip it. And that's going to be true for both tangent and cotangent. No matter what angle, let's go to 135 and then 225, we're going to see that the cotangent value flips from positive to negative. Obviously, it's going to stay the same at 180. You can't flip that. If we go from 90 to 270, it's going to remain 0, because negative 0 is the same as positive 0. So that's the patterns for even and odd identities. Sine of negative theta is equal to negative sine of theta. Cosecant of negative theta is equal to negative cosecant of theta. Cosine of negative theta is equal to positive cosine of theta, meaning it's even. Same for secant. And finally, tangent and cotangent are both odd, meaning tangent of negative theta is equal to negative tangent of theta, and cotangent of negative theta equals negative cotangent of theta. This is why it's very important to visualize the unit circle and notice these patterns. As we flip the triangles, it will help you remember these even and odd identities so that they won't be so abstract. That's it for explaining the even and identity trig in terms of trig functions. If you have any other questions about this, let me know.